All right, so a scalar quantity is a quantity that can be fully defined by just a numerical value. Okay, so a measurement which is fully defined with only a numerical value. And so some examples of that would be like temperature, okay, so if you measure the temperature outside, you get a numerical value, that's all you get, okay? Let's see, the mass of an object, like some number of kilograms, okay? Let's see, a distance, a speed, so a distance like measured on the odometer in your car. It tells you just how far your car's gone. It doesn't tell you anything else about the direction of travel, how fast you move to travel that distance or anything like that. The speedometer measures the speed of your car, fully defined by just how fast you're going, okay? So at any instant in time, it'll tell you I'm going this fast, and that's all it tells you. It doesn't tell you what direction you're going, it doesn't tell you how it's changing over time or anything like that. And so those are all defined, would all be considered scalar quantities, okay? Now there's lots of others, but those are just some examples, all right? So, a vector quantity, all right? So a vector quantity has more information along with it, okay? So a vector quantity is a measurement that has a size, okay? And a lot of times the term that's used for size is magnitude. Magnitude, okay? And a direction, okay? So it has to have both pieces of information to be considered a vector quantity, all right? And the ones we're going to use most the time in this class would be a displacement. All right. And a displacement is basically tells you how far are you from where you started and in what direction. Okay, so it's a straight line. All right, so for the example here, if somebody's hiking in Hawaii, and the black line is the path which they hiked, okay? So they went up on went up on the top of the mountain here, came down this side, went near the down near the beach this way. They turned and they there. Okay, so these would all be individual displacement vectors. But if you wanted to know, well, what was this person's displacement? If this is my starting point and this is my ending point, okay, a displacement would be how far are they from where they started, and in what direction is that distance, okay? So if this is my east, north, west, south, okay? What we're looking for is what is this angle, okay? That would be my direction. So how far would be, use the scale down here, measure how far they've traveled, okay? Measure, use the protractor, measure that angle, all right? And by having both of those pieces of information, that would be my displacement. That's a vector quantity. It has a magnitude, which is the size of that straight line, okay? And it has a direction, which is measured, using our protractor, or calculated using the trig function, okay? So that's an example of a vector quantity, okay? We'll also be using velocity, acceleration, and the other main one that we'll be using are forces. Okay. All right, we haven't got the forces yet, but we have, we will deal with displacement, velocity, and acceleration over the next couple of weeks, and then we'll move into forces. All right, so those are our main vector quantities, but anything that has a size or a magnitude and a direction is considered a vector quantity, okay? All right, so that's the difference between the two. Scalar is fully defined by only a numerical value. How big is it, okay? And then a vector quantity has a magnitude and a direction, okay? All right. So what we're going to do is we're going to look at, well, if you have more than one vector, and we're going to add them together. So how do you add vectors together, taking into account the size and the direction of those vectors? Okay. So, all right. So the example here is a person walks. Okay, so it starts here at the origin. A person walks 9 blocks east. Okay, then they turn and walk 5 blocks north. And the question is, what is their displacement? How far are they? So if you were to fly in a helicopter in a straight line, how far are they from where they started, and in what direction? Okay. Now, mathematically, this one's a pretty simple, straightforward kind of problem. All right. 9 blocks to the east. They turn. They go 5 blocks north. Okay. And the question is, what's the hypotenuse? How far are they from where they started? What's the length of this resultant? Okay. So another term that you need to know is resultant. And that's just the word or the term used for the result you get when you add vectors together. Okay? So if you add 2 or more vectors together, that answer is called the resultant. Okay? It's kind of just a generic term. All right? So if I had 2 distances that I'm adding together, the resultant would be that displacement. Okay? If I have 2 velocity vectors that I'm adding together, that resultant would be the total velocity of that of those 2 vectors. Okay, let's say I have 4 people playing tug of war. Okay. And they're pulling in all different directions, okay? 150 pounds, 50 pounds, 100 pounds, 75 pounds. If I add those together, the answer would be the resultant, okay? What would be the resultant force of those added together, okay? And so that's just the generic term for the answer that you get when you add vectors together. Okay? And when I say resultant, it is considered a vector, all right? And so if you're asked to solve for the resultant, you need two pieces of information. You need the magnitude of it, and you need the direction of it, okay? And when I say magnitude, it's the size or the length, okay? And when I say direction, I'm asking for an actual angle measurement. Okay, an actual angle measurement using this frame of reference, okay? Where to the right, positive x is 0 degrees, and the angles are measured counterclockwise. So this would be 90 degrees, this would be 180 degrees, this would be 270 degrees, okay? That's our frame of reference we're really using for our measurements, okay? Now if you look at the protractors that are on the table, how many degrees do those protractors, what's the maximum angle measurement on those? Right, 180. So those will be good to measure, you know, up in the first and second quadrant. Okay. But if your resultant or your vectors are in the third or fourth quadrant, then you have to turn it over, okay, and add 180 to it. Okay. So like if I'm talking about this one, 180 plus 45, all right, 225 degrees. If I'm looking at this one, okay, 270 or 180 plus, well, it's kind of this one, there we go. 180 plus 140, all right, so whatever that is, 320, okay, all right, so that's what we're talking about when we talk about the angle measurements. All right, so in this case, this one's pretty easy. If we can do this one mathematically, it's called an analytical solution. How would I find the length of the black line there? Yeah. Right, Pythagorean theorem. 5 squared plus 9 squared, take the square root, and you get like the distance of 10.3 blocks. Okay, and then how would I get that angle measurement? Okay, well, using the trigonometry, I could use inverse tangent. I've got the opposite side, I've got the adjacent side. All right, so I could, you know, the tangent of that angle, opposite over adjacent. So the angle would be the inverse tangent of 5 over 9, okay, 29.1 degrees. Okay. So, all right, that's the basics of our vector addition. That's going to be the end point. And so if I ask, well, what's the resultant? Okay, my resultant would be a displacement of 10.3 blocks at 29.1 degrees. So you have to have both pieces of information for the answer, okay? In the, you know, in your book or in most print work, when they're wanting to show you that this is a vector, then it's going to be in bold print, okay? It's kind of hard to do bold print on the board, so what I'll do is, if it's supposed to be a vector, I'll put a little ray over the top of it, and that's the symbol that this is a vector quantity, and it has to have both magnitude and direction. Okay. All right. So that's why I did a review of the trig, you know, a couple of days last week. because we're going to be using it when we add vectors together. All right. Now, I put rulers and protractors on the table because we're going to start by doing vector addition graphically. Okay, and so you'll need a pencil and paper. So that's your notebook. All right. So what we're going to do is we're actually going to draw them to scale, and then measure the lengths and use the protractor to measure the angle. Okay. So what I'd like you to start with is, okay, so this is called the head to tail method. When we add vectors together head to tail, you add vectors by the following steps. Okay, you draw your first vector. So basically you start with your coordinate system, you draw your first vector, the tail. Okay, so on the vector we're going to use a ray to represent a vector. Okay, so this is my vector. This is the tail, and this is the head of the vector. Okay, so think of it kind of like an arrow. All right, so down here would be where you have the feathers on the arrow, the tail of it, and this would be the tip, the point that shoots forward. That's what we call the head. So you start with drawing a frame of reference. Draw your axes, x and y axis. And in this case, you start with once you draw your axis, then you're going to draw a line that's 9 units long. You pick what scale you want to use. So if you want to use one block is 1 millimeter, then you draw it 9 millimeters long. If you want one block to be equal 2 millimeters, then you draw it 18 millimeters long. Okay, so actually get your ruler. Okay, so get a ruler and draw your x and y axis. Get a ruler and draw a line along the x-axis that represents 9 blocks. So draw an x and y axis, and then along the x-axis, going east, draw a line that represents 9 blocks. So you can draw 9 millimeters long, 18 millimeters long. You decide what kind of scale you want to use. All right, then where that vector ends, at the head of that vector, that's where we're going to draw the tail of the second vector. All right, so it will be helpful in the future to go ahead and draw a second x and y axis right there at the head of that vector. And then we want to draw a second vector that's 5 blocks north. Okay. North is 90 degrees straight up. So use the same scale and draw a line that's 5 blocks north. Okay, they're going to get a little harder because we're going to change. They're not all going to be right angles. Okay. All right. Everybody have those 2 lines drawn? All right. So the third line now is draw the resultant. Okay. So the resultant is, the tail of the resultant is the tail that starts at the tail of your first vector. Okay, so you start with the tail there, and the head of the resultant will be at the head of the last vector that you drew. Okay, so it's always tail the head, okay, from where you started to where you ended. And so, using your ruler, measure the length of that line. And whatever scale you use, determine how many blocks that is. So I ended up with 10.5 blocks. Okay, so that's my magnitude. And then you need to measure the direction. So measure this interior angle. I get about 29.5 degrees. So my resultant vector, my displacement, 10.5 blocks. At 29.5 degrees. Okay. Now, I mean, this is, again, it's not, the accuracy depends on, the accuracy with which you draw your lines, scale. The accuracy to, is this truly a 90-degree angle? Did you make it 90 degrees and make sure that the right triangle right there, and turned it 90 degrees? Drawing that line straight and measuring it accurately. Converting it back to the number of blocks using whatever scale you use. Okay. All right. That's the easiest type of graphical addition here because they're at right angles. Okay. All right, and so any questions with that? Okay, we're going to do a second example. All right, this one actually has 3 vectors. All right, so this is the graphical technique for adding vectors to find the total displacement of a woman who walks the following 3 paths on a flat field. First, she walks. Okay, so number 1 is 25 meters at 49 degrees, north of east, okay, north of east. We'll talk about that in just a minute. Then she walks 23 meters at a heading of 15 degrees north of east. So her second displacement vector, 23 meters at 15 degrees north of east. All right. And then she turns and walks 32 meters at 68 degrees south of east. So her third displacement, 32 meters at 68 degrees south of east. Okay, so strategy, represent each displacement vector graphically with an arrow. Okay, they say label them A, B, and C, so A, B, C, okay. Making the links proportional to the distance that are given, and at the direction that's specified. The head-to-tail method outlined above will give a way to determine the magnitude and direction of that vector. Okay, so let me blank the screen out, and we'll do that one together. Okay, now on the directions north of east, so this is east, this is north. So if it says some value north of east, well, it's north of east, so that means you start with east and you go north of east, okay? So the first vector is 49 degrees north of east, so it's in this first quadrant, okay? The next one's 15 degrees north of east. So again, you start with east and you go up north, okay? It's also up here in the first quadrant, okay? The third one is south of east, okay? South is here, so you go out east, but this time you go south, and so the third one down here is 68 degrees south of east, so it's down here in the fourth quadrant, okay? So when you draw that third vector, it's going to be pointing down into the right, down the fourth quadrant, all right? So that's what the terminology means, north of east, south of east, okay? If you're using this connotation, you might see it just as 49 degrees, okay, a positive 49 degrees, a positive 15 degrees. You could see this in two different methods. You could see it as a negative 68 degrees, okay? Down here, here's 0, counterclockwise is positive, so clockwise would be negative, so you can be down 68 degrees like that. Or you could see it as 200 and a positive 238 degrees. Okay, so that would be here, all the way around in the fourth quadrant, pointing down that way. So these are all equivalent angle measurements for 68 degrees south of east, okay? And these will be important when we start doing it mathematically or the analytical method. But, so just wanted you to see there's different ways to represent the same angle. All right, so let's do this one graphically. So we're gonna draw three different vectors. Okay, so start with an X and Y axis. Okay, and we're gonna draw vector A. So it needs to be 25 meters long at 49 degrees up in the first quadrant. So set your protractor and measure 49 degrees. Okay. Does anyone need any help using a protractor? You know where the 0 mark is? You know where, when you set it down here and how to measure the angles? I don't know your protractor skills, so if you need some help, let me know. Okay, and draw it 25 long. All right, so there's 25 meters and 49 degrees. All right, so that's A. All right, now where would I draw B? Well, we're doing it the head to tail method, so here's my head, that's where I draw, that's where I start my next vector. I'm adding the head to tail. So draw another X and Y axis. Make sure it's, parallel, that all the lines are parallel with your first axis. So make sure they're square, straight up and down, right and left. Okay. So the next one is, this was B. Okay, so I need to measure 23 meters at 15 degrees. Okay, so you set your protractor here, measure 15 degrees. And it's 23 long. Okay, so 23 meters long at 15 degrees. So far, so good. Any questions? All right. Then we need to draw letter number C, letter C, vector C. So draw a new X and Y axis. Okay, right at the head of that second vector, because we're adding them head to tail. Okay, so here's the tail, here's the head to tail, head to tail. So this is vector C. 68 degrees south of east. So turn your protractor over. Measure 68 degrees south of east. That's down the fourth quadrant. And it is 32 long. So there's 32 meters at 68 degrees south of east. So that's adding them together. So now we need to find the resultant. Okay. How do we find the resultant? Well, the resultant is drawn from our starting point. So here's our starting point. The tail of the first vector. And we draw it to our ending point, the head of our third vector. So that's where we draw our resultant. So use your ruler, draw a straight line. All right, measure its length. So its length was, I got 50.5. And then you need to measure the angle. So it's in the fourth quadrant, barely in the fourth quadrant. So turn your protractor upside down. Line it up using that first quadrant, that first angle, first reference system that you drew, and I get about 6 degrees or so. Angle about 6 degrees. So my resultant here, 50.5 meters at 6 degrees. Okay, now there is some, room for error because your pencil has thickness to it, and determining where you stop the lines. I mean, you need to draw them as accurately as possible. On these graphical methods, I'll give you like a 5% margin of error. Okay, 5% of 50 is like 2.5. So it could be as small as 47.5 and as large as 52.5. That would be within 5% margin of error. But the angle, 5% of 6 is, about half a degree. So it needs to be, pretty close to that value. All right, so if we look at the notes here, all right, so a little bit different scale, but you can see they got about the same answer. All right, I got 6 degrees, they got 7 degrees. That's what, I give that to you within that, a little outside the margin of error, but my protractor only measures to the nearest 5 degrees, so that's pretty good with that, okay? Your protractors measure down to the nearest whole number of degrees, so yours should be fairly close. All right. So that's the graphical method of vector addition. So use a ruler. All right, so at the end of the notes, okay. That graphical method is summarized. Choose a scale and draw your coordinate system. Draw the length of the first vector to scale at the correct angle. Draw a similar coordinate system at the tip of the first vector. That could also say the head of the first vector. Using the same scale, draw your next vector. Okay, repeat for all remaining vectors. Draw the resultant from the origin, the tail of the first vector, to the tip of the last vector. Okay, the resultant should always point from where you started to where you ended. Okay, measure the length of the resultant and use the same scale to determine its magnitude. And then use your protractor, measure the resultant's angle at the origin, measuring from 0 degrees to the resultant. Okay. All right, so we